Hello and welcome back. Well, students, in the last class we talked about hybridization and we did different type of hybridizations. In this class, we'll be talking about dipole and dipole moment. So, our topic today is dipole and dipole moment. Let us see what does dipole means. Suppose I have got a covalent bond and that bond is formed between two different elements like between H and Cl. So here I have got a covalent bond formed between a less electronegative and a more electronegative element. We know that electronegativity is a tendency of an element to attract the bonded pair of electron toward itself. Chlorine is more electronegative, so chlorine will attract the bonded pair of electron toward itself. Chlorine will acquire a negative charge and hydrogen will acquire a positive charge. So in this bond between hydrogen and chlorine, we are getting two poles, that's a negative pole and a positive pole. This phenomena is known as dipole, or we can say such a bond is known as a dipole. So here we can see that on HCl bond we have got a dipole where one of the atom has got a negative charge and the another atom has a positive charge. So what is a dipole again? In a bond connecting two different elements, the bonded pair of electron move toward more electronegative element. Thus the more electronegative element acquires a negative charge and a less electronegative element acquires a positive charge. This separation of charge leads to the formation of two different dipoles. This is known as dipole. This bond is known as dipole where you got two different poles. So in almost all heteroatomic molecules where a bond is connecting two different elements, we have a dipole. Now what is a dipole moment? When we talk about a dipole moment, there is no phenomena like dipole moment. You will not have any phenomena like dipole moment. It's a measurable, actually in bond you do not have dipole moment. Dipole moment is a quantity which we measure. So what is dipole moment? It is the product of charge and the distance between the charges in a dipole. Now suppose here in this case, chlorine has got del Q negative charge and hydrogen has got del Q positive charge. So I can say the magnitude of the charge is del Q and suppose the distance between them is d. So I can say here in this case that dipole which I am representing by mu is actually equal to del Q into d. So dipole moment is a product of charge into distance between the charges. A dipole moment is always a vector quantity. That is, it not only has a magnitude but also direction. Well, students, if we talk about the standard unit of dipole moment, the standard unit of dipole moment is a debye. Now what's debye? 1 debye we can say is equal to 10 to the power minus 18 electrostatic unit centimeter. Here in this case, I am representing the charge in terms of electrostatic units and the distance between the charges in centimeters. So 1 debye is equal to 10 to the power minus 18 electrostatic unit centimeter. Or I can say 1 debye is equal to 3.33 into 10 to the power minus 30 coulomb meter. In this case, I am representing the charge in terms of coulomb and the distance between the charges in terms of meter. So it is 3.33 into 10 to the power minus 30 coulomb meter. Now when I am saying that dipole is a vector quantity, that means direction also matters. in calculating dipole, I will show you some of the molecules where we'll have zero dipole moment. So we'll see zero dipole moment. Here I'll show you compounds like BeCl2. Chlorine is more electronegative, so chlorine will acquire a negative charge. So on beryllium chlorine bond, the dipole will be like this. On this bond, the dipole will be like this. Both these dipole, they'll cancel out each other. That's why BeCl2 will have zero dipole moment. Likewise, if I talk about BeH2, same goes with BeH2. You'll have a dipole moment like this. On this bond, dipole moment like this, zero dipole moment. Likewise, if I talk about BF3, which is trigonal planar, the molecule is like this. The dipole moment of this BF bond is like this. This BF bond is like this. So their resultant dipole moment is like this, which is cancelled out by this BF bond. Hence the resultant dipole moment is zero. Likewise, we can have carbon dioxide molecule also. CO2 is like this. Oxygen is more electronegative. So carbon oxygen bond will have a dipole like this. And here the dipole like this. Well, students, I am representing a dipole moment by an arrow, where the head of the arrow indicates the negative terminal and the tail indicates the positive terminal. So in CO2, the dipole moment of half of the molecule gets cancelled out by another half. That's why it has got a zero dipole moment. I'll give you another example, that is of, say, alkanes. All alkanes, they have zero dipole moment. Like I have methane. It is tetrahedral. So its structure is like this. If I talk about carbon-hydrogen bond, the dipole moment is like this. So the resulting dipole moment is in this direction, which gets cancelled out by that of another carbon-hydrogen bond. That's why all alkanes, see, any compound which has got a zero dipole moment is said to be non-polar. So polar compounds, they have a dipole moment, and non-polar compound, they does not have a dipole moment. Now since CH4 has got zero dipole moment, it means it is non-polar. Likewise, if I talk about carbon tetrachloride, CCl4, that again is tetrahedral. The only thing is the head of the arrow will project in a different direction toward chlorine, because chlorine is more electronegative. So it is like this. The resultant dipole moment of 3 carbon chlorine bond is in this direction, which gets cancelled out by the second one, which is at the top, and that's why it has got a zero dipole moment. So these are some of the molecules which have got zero dipole moment, and that's why they are known as polar compound. Now we'll come on to the question based on this. First we'll see these are your textbook questions that among BF3 and NH3, in fact I'll correct it, not NH3, it is NF3. Among BF3 and NF3, BF3 has zero dipole moment, while NH3, again it's not NH3, NF3, while NF3 has a positive dipole moment. Why? Well, student, when this question is asked to you, you can draw a structure of BF3, which I have shown you here. You can draw this structure, and you can show that it has got a zero dipole moment. Now, what about NF3? Let us have a look at NF3 molecule. NF3 molecule is like this, where you have a lone pair of electron, and these are the three NF bonds. It is pyramidal in symmetry. Fluorine is more electronegative, so NF bond will have a dipole moment like this. This NF bond will have like this. This NF bond will have like this. So their resultant dipole moment is in this direction. Well, lone pair itself has got a weaker dipole moment. So we can say the dipole moment of lone pair is in this direction. If we subtract them, we'll have a weaker dipole moment in this direction. Again, the three NF bonds are polar, where fluorine is more electronegative. So you have dipole on these three NF bonds. So as a result of that, you will have a resultant dipole moment in the downward direction, which is slightly cancelled out by that of the lone pair. So you'll have a weaker dipole moment in the downward direction. So NF3 will have a positive dipole moment, but BF3 will have zero dipole moment because BF3 is trigonal planar, where the resultant dipole moment of two BF bonds is cancelled out by that of the third. The next question of your textbook is, give reason why NF3 has a weaker dipole moment while NH3 has a higher dipole moment. Well, in order to explain this question, I'll draw the structure of NH3 beside NF3. NF3, you can see this is NF3. Now let us have a look at NH3 molecule. NH3 molecule is very similar to NF3. You will have a lone pair of electron and you'll have three NH bond. But here in this case, nitrogen is more electronegative than hydrogen. That's why the dipole moment will be like this. Here it will be like this. If I add the dipole moment of these three NH bonds, the resultant dipole moment will come in this direction. And in the same direction, we have a weaker dipole moment of lone pair. So both of them, they'll get added and you'll have a resultant dipole moment in this direction. So in NF3, the resultant dipole moment of three NF bonds is in opposite direction to that of lone pair. That's why you'll have a weaker dipole moment because they'll get subtracted. Whereas in NH3, the resultant dipole moment of three NH bond is in the same direction as that of lone pair. So they'll get added, and in NH3, you'll have a higher dipole moment. Third question I'll tell you, that again is of your textbook. And according to that, tri-atomic molecules can exist either as linear or in bent symmetry. Show according to dipole moment that CO2 is linear while H2O is bent. So we'll explain that triatomic molecules. I'll give you an example for that. Suppose I have three atoms. Here I have, say, A, which is joined to 2B. So the structure can be either linear or it can be bent. Linear means 180-degree angle, where the dipole moment of one half of the molecule will cancel out another half. So resultant dipole moment will be 0. Whereas if I either decrease this angle from 180 to lesser, or I increase this angle from 180 to higher, the symmetry will come like this. It will be like this. This one is bent. In bent, there is no zero dipole moment. You'll have a positive dipole moment in bent symmetry. So we'll see if we talk about water molecule. So suppose this is the bent symmetry which we have got. If the dipole moment is like this and this dipole moment is like this, both of them they will get added and you'll have dipole moment in this direction. On the other end, if A is more electronegative and the dipole moment is like this dipole moment is like this, then also you'll have a positive dipole moment in this direction. Water molecule has got a positive dipole moment. That means water is not linear. Now let us have a look at CO2. See, in CO2, since it is linear, the dipole moment of half of the molecule gets cancelled out by another half. That's why it has got zero dipole moment. So since CO2 has got zero dipole moment, that automatically proves that CO2 is a linear compound. Now if we talk about water molecule, the structure of water molecule is like this, where you have one lone pair here and another lone pair here. The dipole moment of this lone pair is like this, that of this lone pair is like this. So you'll have a resultant dipole moment like this. Likewise, if we talk about oxygen-hydrogen bond, you'll have a dipole moment like this. Here also you'll have a dipole moment like this. So resultant dipole moment is like this. So dipole moment of lone pair and bond pair will get added and you'll have a positive dipole moment. So since water molecule has got a positive dipole moment, that means it's not a linear molecule. In fact, it's a bent molecule. CO2 has got a zero dipole moment. That means it is not bent. It is linear. So two possible symmetry for a triatomic molecule is either linear or bent. In linear, you'll have a positive dipole moment, whereas in bent, you'll have zero dipole moment. So this is all about dipole moment. Next, I'll teach you something about the coordinate bond. So we'll see coordinate covalent. Coordinate covalent, also known as dative bond. Coordinate covalent or dative bond. Well, student, you should learn this bonding seriously, because although you've got a very small topic in 11th standard, but you've got a complete chapter in 12th. In 12th standard, in book 1, the last chapter is coordination chemistry, and that is basically based on this bonding. Now let us have a look at this bonding. Now suppose I have ammonia molecule like this, NH3. When I talk about ammonia, I know that nitrogen has got a lone pair of electron in this. I have already taught you the structure of ammonia in hybridizations. So here you have a lone pair of electron on hydrogen. Now suppose I have got another molecule, that is BF3 molecule. In ammonia molecule, the octet of nitrogen is complete, whereas in BF3, the octet of boron is not complete. So nitrogen will donate its lone pair of electron to boron. Complete lone pair of electron will be donated. It will donate its lone pair of electron to boron, so that the octet of boron will get complete. So boron will also become stable. So this is a different type of bonding. In coordinate bonding, what happens? The lone pair of electrons are donated by an atom to an electron deficient atom or molecule or ion. So in coordinate bond, a lone pair of electron is donated by an atom to another electron deficient atom, ion or molecule. The atom which donates its lone pair can donate only after completing its own octet. If the octet of the donor atom is not complete, it cannot donate its lone pair of electrons. So first it will complete its own octet. I'll give you one more example. We all know that this is ammonia. If I react ammonia with an acid, it gets converted to ammonium. Now what's the structure of ammonium? It combines with H positive ion from the acid and will lead to the formation of a compound like this, where it will donate its lone pair of electron to H positive ion. Now, since it is donating its lone pair of electron to H positive ion, the positive charge will move on whole molecule. So we'll write the positive charge like this. So many times you have seen a compound written like this, H4 positive, that is ammonium. So in ammonium molecule, you have three normal covalent bond, but one of the bond is coordinate covalent or dative bond. Likewise, if we talk about a water molecule, now here I have a water molecule and H positive ion from an acid. So it will donate its lone pair of electron. It will donate its lone pair of electron to H positive ion, leading to the formation of hydronium ion. So like ammonium, you have got hydronium ion, which is H3O positive. Again, what's a coordinate bond? A coordinate bond is formed by the donation of lone pair of electron by an atom to another electron deficient atom, ion or molecule. A coordinate bond is always represented by an arrow, where the head of the arrow indicates the acceptor atom and the tail indicates the donor atom. An atom can donate its lone pair only once its own octet gets complete. So this is what coordinate, covalent or dative bond is. After this, we'll move on to the next topic, and that is resonance. We'll see resonance. Here I'll show you some of the resonating structures also. What is resonance? Resonance can very well be explained by taking an example of benzene molecule. Now here, suppose I have a benzene molecule. We call it benzene, but it can also be called as cyclohexatriene. Now the question comes to our mind, what's the difference between benzene and cyclohexatriene? Well, if benzene is like this, then it means three of the carbon-carbon bond has to be double and stronger, whereas this three has to be single and weaker. Whereas it is observed that all carbon-carbon bonds are neither purely double nor purely single. They are 1.5 type bond in strength, in length. That means there are molecules in which all their chemical and physical properties cannot be explained by a single structure. And we need to draw more than one structure to explain all their chemical and physical properties. This phenomena is known as resonance. So in benzene also, we need to draw its another structure. And that structure is like this. So these two structures collectively represents all chemical and physical properties of a benzene molecule. If I join them, I'll get a resonance hybrid structure. A resonance hybrid structure of benzene can be drawn like this, where I draw a cycle or a circle of pi electrons. So what these two structures are? These two structures are the contributing structures, also known as canonical form. Whereas this structure is the resonance hybrid structure. Resonance hybrid structure. So what is resonance? Again, there are certain molecules in which all their chemical and physical properties cannot be explained by a single structure, and we need to draw more than one structure to explain all their chemical and physical properties. This phenomena is resonance. The structures which we draw to explain all their chemical and physical properties are known as resonating structures or contributing structures or canonical forms. All contributing structures, they have same energy, they have same number of sigma and pi bond, they have same charge, they have same number of different atoms, and they have same energy. Whereas the resonance hybrid structure has got a lesser energy. It is at lesser energy. And the difference of energy, I'm writing E of contributing structure, energy of hybrid structure. And as I told you that hybrid structure is always at lower energy. So I can say resonance energy is always the difference of the contributing energy, contributing structure, energy of contributing structure, and energy of resonance hybrid structure. So the difference of energy between the resonance hybrid and one of the contributing structure is known as resonance energy. Well, we'll see the resonating structure of some of the compounds, like we'll see the resonance structure of CO2. We can draw CO2 like this. All resonating structure, they basically differ from each other with respect to the position of pi electron. The pi electron, they keep on moving and you have different resonating structures. So in CO2, when the pi electron will move toward one of the oxygen, that will acquire partial negative charge. The another oxygen will acquire a partial positive charge. Likewise, here in this case, this will acquire partial negative and the another one will acquire a partial positive charge. So these are the resonating structures of CO2. Next we'll see resonating structure of carbonate ion, that is CO3 2 negative. Well, a carbonate ion can be drawn like this, CO3 2 negative. The pi electron and charge both will move. So the next structure will be like this. Still next structure will be like this. And if I combine all these three structures, I'll get their resonance hybrid structure. So I can draw the moving pi electrons like this by these dots. And the small negative charge can be represented like this because negative charge is moving on all the oxygen atoms, so it can be represented like this. So these are the resonating structures of carbonate ion. Likewise, I can draw resonating structure of nitrate ion, that is NO3 single negative. In NO3 single negative, the structure is like this, O negative, double bond O, and coordinate bond O. So this double bond will now move here, O negative will come here, and coordinate bond will move here. Again, the double bond will come here. When the double bond is coming here, the O negative will come here, and the coordinate bond will come here. These are the three resonating structures. If you want to draw a resonance hybrid structure for this, again you can draw it like this. Electrons, they are moving, so you can represent them by these dots, partial double bond character. The small negative charge can be represented by delta negative. So these are the resonating structures of nitrate ion. Similarly, you can draw a resonating structure of SO2 molecule. See, SO2 molecule has got a structure like this, where it has got a double bond with oxygen and a coordinate bond with oxygen with a lone pair of electron. Next resonating structure will be like this, coordinate bond, double bond, and lone pair. So its hybrid structure can be single bond O. The dot is representing the movement of pi electrons and small negative charge on both the oxygen atoms. So this is some of the resonating structure, and this is how you can make more resonating structures. So many times resonating structures of carbonate, nitrate, sulfur dioxide, carbon dioxide, they are asked in the exams. So you go through all these resonating structures. So in today's class, what we did dipole and dipole moment. We talked about coordinate bond. We talked about resonance. In the next coming class, we'll be doing the drawbacks of valence bond theory and molecular orbital theory along with formal charge. So this is what we were scheduled for today. That's all for today. Please be in touch in case you have any doubt. Contact me, send me a question. I'll send you back the answer. And do subscribe my channel so as to get all the notifications on time. Thanks for watching. Thanks a lot.